Hello, welcome back. In this segment, I will explain how ElGamal scheme is vulnerable to signature forgery. So in the ElGamal scheme, you are given a signature R, S for a given message M. The question is, can you find new signature for a different message without having the private key? Okay, that is the question we are going to answer. Luckily for us, that question is answered on the paper itself. You can see here, this portion of the paper talks about given a signature, find another message and signature such that the validation will be successful. Okay, I am going to just make use of the paper for this discussion. You select three numbers A, B, C such that AR minus CS is relatively prime to P minus 1. The reason we use P minus 1 is that order of the group ZP is P minus 1. Okay. And if you select these numbers A, B, C in such a way that these properties are true, then you can successfully enable a verification, even though you don't have the private key X as part of the signature. As you can see, for this R, S, and M, I must say R prime, S prime, M prime, alpha power M prime is same as Y power R prime power S. This is exactly what we need for digital signature verification. Remember, for digital signature verification, the constraint we need to have is alpha power the message, whatever message we have, is equal to Y power or R power S. That's the general structure we need for the message M to be valid, meaning corresponding to the digital signature pair R, S. Okay. So instead of R, S, M, we have numbers R prime. That means the same number R prime is used here, and S prime. And you get M prime here because we are trying to generate digital signature for a new message. You see here, we are generating a digital signature for a new message M prime that corresponds to R prime, S prime. Okay, so this attack is inherent in many digital signature schemes. One possible way to avoid is to not use M directly. The message M should not be used directly for signature, but apply one-way function, something like hash functions. Okay. We don't go into the details of what type of hash functions we need to use, but at this point, it's important to know that the raw ElGamal scheme that we have been discussing is vulnerable to existential forgery. You could construct digital signature for some arbitrary message, not for the message that you choose necessarily, because as you can see, the flow is you have to have R prime, S prime first, and then only you can update an M prime. You can't easily go other way around. Say you have a nice message you would like to sign, that is difficult to do. Okay, but what is easy to do is you can create existential forgery, meaning you can eventually get R prime, S prime corresponding to M prime, but M prime may not be useful for you. That's a different story. Nevertheless, it's interesting to show existential forgery in this scheme. Okay, that's basically it. I have already implemented this as part of a proof of concept. I created a forgery which takes P, G, M, R, S, Y. We have talked about all of these in the past. P is the group that we are playing with. G is the group generator. M is the message. R and S corresponds to the signature of M. Y is the public key. The goal is to generate a new RSFM. You can see underscore F means forgery. That's the reason I put underscore F. Okay. And I'm just doing the algorithm that was discussed on the paper. I randomly select A, C such that A times R minus C times S is congruent to P minus 1. That's this part. Once I have this, and then I'm able to construct RSM. These are all forgeries, right? This is basically, I'm signing an arbitrary message using RFSF as the input. As you can see anywhere here, first of all, in the forgery part, there is nowhere I'm using the private key X. Okay. And during the verification, I'm successfully getting the verification. Okay. I pass one signature, one message, right? And obtain different signature for a different message. Okay. That's basically it. Thank you very much for your attention.